In this session, we discuss the relation between moment of inertia and torque. As you all know, the torque is nothing but is the rotational analog of force or rotating effect derived from the force. Okay. Now, to get the relation between the torque and moment of inertia, I consider a rigid body which is rotating about an axis with the increasing angular velocity. Means angular velocity omega is not constant. Is not constant. It's gradually increasing. That means the rotating body is having an angular acceleration. So angular acceleration, I take it as alpha. So the body is rotating around with an angular acceleration alpha. Angular acceleration. Okay. And this angular acceleration is assumed to be constant for the rotational motion considered here. Now, as the body moves around, each and every mass particles are moving around, and suppose I say that M1 is moving with a tangential acceleration of A1, M2 with A2, like that, Mn as an acceleration An, suppose. Even though the angular acceleration alpha is constant, the mass particles' individual tangential acceleration will be varying because it is found to depend on the distance from the axis of rotation. That means I can consider that acceleration A1 equal to R1 into alpha and A2 equal to R2 into alpha, like that An equal to Rn into alpha, I could write. Alpha is constant. So each and every mass particles angular acceleration is constant, but their individual tangential acceleration will be different as from the equation already known. Therefore, if I write the equation for torque tau, then torque tau can be written as R1 cross F1, okay, plus R2 cross F2 plus etc. plus Rn cross Fn. That means there will be an individual force acting on these mass particles as F1, F2, etc. to Fn, and therefore I can apply the cross product here. But as it is moving around with respect to this axis, the angle between this R vector and F vector will be 90 degrees. They are perpendicular to each other. So I can write this torque tau as R1 F1 plus R2 F2 plus etc. plus Rn Fn. Now it is very simple that torque tau equal to R1 into M1 A1 plus R2 into M2 A2 plus etc. plus Rn into Mn An. Collection of particles is coming like this. So for this will be equal to R1 into M1 into R1 alpha plus R2 into M2 into R2 alpha plus etc. plus Rn into Mn into Rn alpha. So I can write this as M1 R1 square into alpha plus M2 R2 square into alpha plus etc. plus Mn Rn square into alpha or torque will be equal to m1 r1 square plus m2 r2 square plus etc. plus mn rn square into alpha or torque 2, therefore will be equal to I into alpha. That means this can be equal to torque 2, which is equal to sum of mi square into alpha from n I equal to 1 to n. Okay. So this is the relation connecting moment of inertia and torque. Torque 2 equal to moment of inertia into angular acceleration. But when you compare that with the force F equal to mass into linear acceleration. That means wherever mass comes in the linear motion or translatory motion, moment of inertia will be assuming the position in rotational motion. And these two are the corresponding acceleration parameters in the respective motion, I could say. Okay. So this is how the relation between the torque and moment of inertia. Okay. So like this, we can obtain the relation between angular momentum and torque. Okay. Sorry, angular momentum and moment of inertia. So angular momentum and moment of inertia, if I take moment of inertia and angular momentum. Okay. Now for that, I will be considering a rigid body which is moving around a fixed axis. Same case again. I am considering the rigid body moving around the fixed axis shown here, and consider the mass particles m1, m2, mn, etc. As the vertical distance from the axis of rotation for the particles are r1, r2, etc. rn, you can see. Now, as we want the relation between angular momentum and torque, let us assume that the angular velocity omega is constant for the rotation. Okay. So if angular velocity omega is constant, each particle will be having its own linear velocities here, v1, v2 and vn, tangential velocities. Okay. And as we consider the case of angular momentum, okay, angular momentum L is equal to R cross P. This is the formula we had for angular momentum of the rotating body, and R is the vertical distance from the axis and also P is the linear momentum. So if I use this formula for this particular rigid body with n mass particles, I can write which is equal to R1 P1 plus R2 P2 plus etc. plus Rn Pn. See, cross product of course, and R and P are perpendicular to each other, and therefore I can write this as a simple sum like this. Okay. And therefore L will be equal to R1 into M1 V1 plus R2 into M2 V2 plus etc. plus Rn into Mn Vn. Now this can be rewritten as R1 into M1 into R1 omega plus R2 into M2 into R2 omega plus etc. plus Rn into Mn into Rn omega. Because tangential to that linear velocity I have converted into the angular velocity omega, which is constant here. Okay. So this can be written as M1 R1 square omega plus M2 R2 square omega plus etc. plus Mn Rn square omega. So can be written as M1 R1 square plus M2 R2 square plus etc. plus Mn Rn square into omega, that is angular momentum L. So the bracket quantity, as already you know, this can be equal to the moment of inertia I of the rigid body about the axis of rotation. Therefore, angular momentum L can be written as I omega here. So angular momentum L is equal to moment of inertia into angular velocity. So if I compare that with the linear motion, linear momentum will be equal to mass into linear velocity. Again you can see that the mass comes in linear motion, again moment of inertia comes in the angular motion. So in every sense you can compare the linear motion with the angular motion like this. So this equation is very, very important. This can be taken for analyzing the rotational motion of certain types of objects or certain situations. And angular momentum conservation also can be understood in terms of L equal to I omega. So in this video you understood the relation between moment of inertia and torque, and moment of inertia and angular momentum. Okay.